This lesson is going to be about the integral test or convergence, and also it will be about estimation of sums. So these will be two separate ideas but linked together with integrals. So the first thing is that we've defined limits, we've defined convergence. Our next goal is to decide on the convergence of less clear sequence and series. So when we look at a series and we don't already have it as geometric or harmonic or something like that, what are we going to do? Two such series are here. One is as n goes from 1 to infinity of 1 over n squared, and one is same deal, 1 over root n. Different function, same infinite sum. So what I'd like you to consider is, let's deal with this one first, 1 over n squared. We could write a function that does that, and that function is 1 over x squared. Right? Important note here is that it touches all of the right endpoints, right, the right sides of our rectangles, and thus is greater than the area of each of these things. And if you're thinking, like, where did this come from to unite this, think about what the area is of that. This area is going to be 1 over 1 squared. This area will be 1 over 2 squared. That area will be 1 over 3 squared. So it's just showing this infinite sum as an area model. Okay. So what we're going to do is we're going to say, hey, I know that this red line here, y equals 1 over x squared, clearly exceeds this sum. If that's the case, then what if I just found the area under the function y equals 1 over x squared? Hopefully you immediately thought integrals. And so we're going to integrate this function. If that gives us a number, then we know that this sum must converge, because this sum is clearly less than the function y equals 1 over x squared. So let's do that. We will, like I just said, this thing is clearly less than the integral of 1 over x squared. And now I should actually, yeah, that's fine. Now what we're going to actually calculate from 1 to infinity, you can see I've kind of started you at that point right there, going from 1 to infinity. So we'll actually add in this area plus the integral 1 to infinity, just to make sure we're adequately accounting for everything that's in this sum. It actually wouldn't be a big deal even if it wasn't there. But so now we take 1 plus this integral, and that would be negative 1 over x from 1. And technically the way that I should probably write this is probably to put a variable up here and then write limit as, like, put a t here and then put limit as t goes to infinity. But I'm actually not going to do that. I'm just going to use a bit of a shorthand, just saying that it goes from 1 to infinity. Okay, and that's just for this part, because that 1 is already there. So negative 1 over infinity, right? Negative 1 over some huge number. If you let that limit, the way I had it written before with the limit, that'll become 0 minus negative 1. So it'll become 1 plus 1, which is 2. And thus, if this integral goes to 2, then this must converge. Okay, so we're going to do the same, a similar process here, but in this case, the function is unfortunately not going to do the same trick. So this will be y equals 1 over square root of x. And you notice over here, the curve was above each of these rectangles. Now the curve is below, so there's some extra amount here, which means this sum is going to be slightly larger than the integral that we're about to calculate. And again, if you're wondering, how did this relate to the picture? It's really just the same exact thing as an area model. So the area of this one would be 1 over root 1, the area of this one would be 1 over root 2, etc. But this curve happens to hit its left endpoints. So now if we take the integral, we already said that that's going to be greater. If we take the integral from 1 to infinity of 1 over root x dx, that will be negative x to the half, not negative. Half, no negative necessary, but there will be a 2 there. And that'll go from 1 to infinity. I don't know why I'm just looking at this thing funny, but it's fine. And then if you let the x term get very large here, subtract that 1, who cares? It's going to be 2 times half the square root of 1. But this thing will make that whole integral will be too big, right? It's going to infinity. And if that is bigger, if this sum of these areas of rectangles is larger than our integral, then that tells me that this thing must diverge. Okay, so now let's generalize into a theorem. And the theorem is as follows. The sum converges if and only if the integral from 1 to infinity of the function converges. So I know we didn't show every which way here. We didn't have an integral that is divergent and then show this deductively. I've just presented a couple of examples for you, and this is true. This is a true statement, though, to say that if you take the integral of the function that's describing this sum, this is when you let a sub n equal some function f. If you are to integrate from 1 to infinity, and you think about it, this kind of makes a lot of sense because of what an integral is and the fact that it is an infinite sum of rectangles. If this thing converges, then you're guaranteed that this one converges, and vice versa. Okay, a couple notes. Usually you just look at the big deal of the theorem and you say, okay, that's the idea. However, the function must be continuous, positive, and importantly, the function must decrease. Okay, and if you're thinking, what's the deal with decreasing? Well, that's what creates these endpoints, and it's like, well, why does it need to decrease? Think about a series. If a series is to converge, its sequence that it's built on must go to 0, right? So we're counting on a decreasing function. So, like I said, f has to be continuous, positive, and decrease for all of this stuff to work. So technically we should verify our assumptions prior to using this theorem every time. We will not be doing that, but each time it would be the best thing to do. Just in the interest of time in the videos, I'm not going to do it for everyone. Okay, so an example. The question is, what's that thing do? Is it convergent, divergent, etc.? So what we're going to do is take the integral, 1 over x squared plus 1, from 1 to infinity, dx. and maybe look at your formula packet or table of integrals or whatever, and you'll find that that's the integral of tan inverse. And when you take the inverse tangent of an infinite number, you end up with pi over 2. Tangent inverse of 1 is pi over 4. So that's pi over 4. I don't even really need to do this calculation out, but that is a lockdown case now that this integral is convergent. Thus, that sum is also convergent. Okay, now another slightly more important example that we're going to use the integral test for, but then it will result in another thing that we can use in our bag of tricks. Remember, we have geometric series that we can test against, we have harmonic series we can test against, and now we have this integral test. But this is going to be one more thing that we can use when deciding convergence and divergence. Okay, that says 1 over n to the p. So p can be anything, and the question is, this thing converges for what values of p? Okay, so I would say it's pretty clear if p is negative, then 1 over n to the negative value would be the same as n to the positive, whatever that is. And the function, clearly if p is negative, we're going to have a divergence. And I think similarly, clearly, if p is 0, we're also going to have a divergence, because that'll be 1 over 1, which is 1 plus 1 plus 1 plus 1 plus 1, which obviously diverges. So we're just going to kind of throw those ones out, and really we're going to think about more so what happens when p is positive. Well, if so, we'll integrate from 1 to infinity, 1 over x to p dx. So take the integral of that, maybe just pause it so that you have the integral. It would look like this, I believe. And then when you substitute in some large number, you need to be thinking about x, like putting those numbers in for x. However, you need to consider what p's are going to help you out. This one will converge only if p is greater than 1. If you're wondering why, if p is greater than 1, then this is negative p, right? Negative, let's say p is 2, or p is 7. Negative 7 plus 1, that'll be x to the negative 6th. Okay, so as we plug a larger number in for x, x to the negative 6th is very small, right? Goes to 0. So that's why we need p to be greater than 1. If p is less than or equal to 1, then it will diverge. Picture, like, let's just say 1. Negative 1 plus 1 is 0, x to the 0 is 1, and now you're infinitely many times you're adding up negative p plus 1. No good. If p is some fractional value like a half, negative 1/2 plus 1 is a half, and eventually, even though it's a smaller power, we're still going to get an infinite amount when we add all those up, or when you substitute in for x. So this thing now is going to be our p series. Okay? So you're going to know, like I said over there, it converges only when p is greater than 1. And now if you look back at it, and you're kind of out of the weeds of the integral detail, when you think about a large p-value here, that's 1 over n to the 50th. Yeah, that's pretty small, right? Each of those terms is getting very small, so when you add infinitely many of them up, it could potentially converge. Side note, if p equals 1, name that series. Hopefully you all at your little desks at home said it's harmonic. It is harmonic because it would just be 1 over n, summed from 1 to infinity. Okay, so that's our P series. So now we have geometric, harmonic, P series, and the integral test. More to come. One thing we can use the integral test for, though, is estimation of sums. Okay? So let's suppose that the limit as n approaches infinity of s sub n is equal to s. S sub n, by the way, I'm saying is equal to change my variables, I equals 1 to n of a sub I. So it's the nth partial sum. If you let n go to infinity of the partial sums, let's suppose that it goes to some s value. In other words, that it's convergent. And this says that that s value is real. Okay, now, the remainder, r sub n, will equal the sum minus the partial sum. So if I said like, oh, I want to calculate this partial sum, or I want to calculate the infinite sum, and I do like the first 52 terms, the remainder would be the actual minus what I've gotten with my first 52 terms. In other words, that's going to tell me how far off I am from the actual convergent sum. Okay, if that's the case, then r sub n will equal a sub n plus 1 plus a sub n plus 2 plus on and on and on. And if you're wondering where that came from, think about a sub, s sub n, remember, is a sub 1 plus a sub 2 plus on and on all the way up to a sub n. So this has the first n terms built into it. What's not built into this is the n plus first and n plus second and n plus third terms. So the remainder is going to be all the stuff I didn't calculate in my partial sum. That is going to be less than or equal to the integral from n to infinity of the function. Again, where the function is defined by a sub n will equal the function. And what's going on here is basically, why is it less than? Well, you've got a similar picture to what we did before, which is kind of like this, where this is n, the area here is a sub n plus 1, the area here is a sub n plus 2, and we're going to be, our function is going to be larger. Okay, now it's also r sub n, which is equal to all that stuff we just said. It's also going to be greater than the integral from n plus 1 to infinity. And if you're wondering why that is, another picture. We're going to start with n plus 1. So that's the n plus first. This will be a sub n plus 1. A sub n plus 2 will be the area of that one. And we've got that picture. So it's pretty much the same thing that we already discussed. But importantly for us, the remainder, which is telling us how far off we were by trying to estimate the sum with the first 52 terms, the remainder is less than that integral and greater than that integral, and thus the integral from n plus 1 to infinity of the function is less than the remainder, is less than this integral, which is a big idea. So this is going to allow us to approximate sums. And what we'll be able to do is not only tell you how far off we are, but we'll also be able to say, okay, if you wanted a certain amount of accuracy, so I'm going to get rid of all this, if you wanted a certain amount of accuracy, here's how far you'd have to go to get that amount of accuracy. Okay, so we're going to approximate, this will be the last thing that we do, we're going to approximate the sum of this using 10 terms. Maybe just have your just sit there and plug away at your calculator until you get there. But what we're basically saying is that up to here, well, no. I could write it that way. What I'm going to do is say that that is close to S sub 10, which means to 1 over 1 cubed, 1 over 2 cubed, 1 over 3 cubed, etc. And you should get approximately 1.1975. By the way, a little side note here, 1 over n cubed is a p-series where p is greater than 1. Thus, we know ahead of time this thing converges, so we're even allowed to carry any of this process out. Okay, now R sub 10, which is the remainder of this. Whatever this thing converges to, 1.1975 is not exactly right. R sub 10 is less than the integral from 10 to infinity of 1 over x cubed. And that integral is 1 over 2 times 10 squared, which is 1 over 200, which is 0.005. So what I know then is my error, or the remainder, is going to be, I'm 0.005 or less away from the actual sum. So if you were doing something that you needed a certain level of precision, you'd look and say, well, I'm only maximum 0.005 off, right? Because the remainder is going to be less than that integral. So we're using this factor here. Okay, so we can also do this. What we can do is reverse engineer this process to say, what if we specified an error of 0.0005. So we wanted to be even more precise. Well, we would say the error has to be less than that, and that's 1 over 2n squared. And just say, okay, set that less than 0.005, and then you can solve. I'll let you do that. But you'll find that n has to be greater than the root of 1,000, which is about the same as 31.6. So what that tells me is we need 32 terms. So here we estimated S sub 10 to be 1.1975. We realized that was 0.005 off maximum. And then we said, what if we specify an even smaller error? Well, then we know the error has to be less than the integral. We did the integral, plugged n in, right? Did the integral, set it to be less than that, and then calculated n, and we found 32. So if you went 32 terms out, you're guaranteed to be that far away from, that far or less away from the actual sum. Okay, so in this lesson we hit an integral test for convergence, and then we used that to study p-series. And after that, we hit estimation of sums, again, using that same approach.